the title of the lecture is Feedback Motion Planning. And listening to your feedback, instead of starting with a broad, big picture motivation, let me start with a specific a case study example, okay? So, so you remember on the midterm, I gave you a question about juggling, right? You just had to think a little bit about trajectory optimization of a juggling robot. Let's think a little bit more about the juggling problem. So juggling is obviously a hugely complex manipulation task. People do it with flair. One of the beautiful things about the juggling robotics literature has been that there's been success in distilling that really hard problem down into simple models. And I really want, as you have thought now about your projects and what you want to do, I think you will be most successful in all these endeavors if you can find a way to capture this thing you care about, this idea you've had, in the simplest possible way, try the tools on that, and then build back up to the complicated model. So the story in juggling is very much, again, a story about the simplest juggling model, which is what I had on the midterm. And then building back up from that. It's called the line juggler. Okay, and it's, you'll remember there was a zero line, there was a paddle and a ball, the height of the ball called B, the height of the location of the paddle was R, and everything works just in the line. So the state space of this thing we're going to be able to write down as B, R, and B dot, and we'll assume that we have direct velocity control of the paddle with some big actuator underneath. So our input is just on the velocity of the paddle. And the other big assumption is instantaneous elastic collisions with some coefficient of restitution. You get most of your energy back. Now we talked about in the midterm about doing trajectory optimization for this, but if you want to do feedback design for this, it's still a relatively high-dimensional nonlinear thing. It's a hybrid system with impacts, certainly under-actuated in the sense that I've got nothing to do to control the ball when the ball's in the air. It's only the moment when it's hitting the paddle that I can have some effect on the trajectory of the ball. Okay? It turns out everything gets a lot easier if we just if we restrict our attention to feedback controllers that take a particular form. So yeah, restitution. Like, so you get the velocity that comes out of the collision is the negative of the velocity that comes in times 0.9, let's say. Right? That's the coefficient of restitution. Okay, so we're going to restrict ourselves to controllers of the form R is, let's say, negative K of B, or more generally, negative K B dot of B. But the point is I'm going to restrict myself to things that are somehow where R is doing roughly what the paddle is doing, but in the opposite direction. These are called the mirror laws. Okay? They're a great idea because they simplify the dynamics considerably, right? So just by virtue of having this sort of mirror law, that I'm doing the opposite of what the ball's doing, I get for free that collisions only occur at r equals 0, b equals 0, b dot less than 0, less than equal to 0, I guess. Right? I'm always going to collide in the same place. The ball's going to be coming towards me. Just all these screw cases go away. Right? And, not surprisingly, the real big win is that suddenly my high-dimensional dynamical system can be described completely on a one-dimensional Poincare map because of this. Right? So if now the whole state can be described by, at the moment of collision, by just the value of b dot. Okay? And the cool thing is that very simple laws, even constant k's chosen properly, can give you stable Poincare maps, right? So the hopes that I can keep things all on one page and still be legible, I'll just so I'm in the negative quadrant now, okay? But turns out you get these beautiful Poincare maps. They always, with the mirror law, they're going to go through the origin. And I'll get an unstable fixed point at the origin. But you can get these globally stable, except for that measured 0 set, fixed points that will stabilize a constant juggling height. Okay? They say essentially globally stable because there's only a measure 0 set where there's one point in the space where I'm not going to converge to the origin, to that stable fixed point. Okay? So this is one of the classic under-actuated hybrid feedback control problems where people have done really nice work and understood the system and produced robots that can do it. To make the robot, so you can build a robot like this in the plane. In practice, you tend to need to stabilize that out-of-plane motion just because it's a physical system. You can't start it perfectly with 0 velocity maybe, or it's hard. Okay, so there's a simple generalization of this. Turns out if my robot is, instead of a up and down motion, is now a paddle like this, where I have some theta dot maybe moving up, and my ball now has both a y component and an x component. Then I can do almost exactly what I did before, and with some sort of small angle approximations, I can still stabilize this by thinking about how to stabilize both parts. The big idea is I can just modify the collision to occur either just above the line if I want the ball to start to move more this way, or just below the line if I want the ball to move more this way, right? And you can put these things together and get nice, practical, stable juggling robots, with this mirror law being the heart of it, and then just a small deviation from it to give me the stability and the out-of-plane motion. And Martin Buehler and Dan Kodacek made all these juggling robots back even in the 80s. This is just showing off doing two at once, because, hey, I'm not doing anything when the ball's in the air, so I might as well hit another ball, right? This is on like an air hockey table that's at an angle, right? Just to help it stay 2D. Okay, and then there's, of course, the same trick that you did to go from 1D to 2D. You can do this in this direction too if you have an extra degree of freedom in your manipulator, and extend it to 3D. And this is Al Rizzi came into the picture, and working with Dan did the 3D version. I might have a particular love for this because my desk was behind the curtain for a little while, sort of. They had done this work before I came, but that robot was at the University of Michigan in the basement when I was there as an undergrad. Wasn't far from the foosball table. Okay, so they got this basic juggling behavior, and then they started. You can imagine a small generalization to that controller, which is very much a feedback controller designed with hybrid analysis and nonlinear control, right? They could generalize that to just stabilize the zero velocity, so they could catch the ball. Palming, I guess, is an important trick for well, at least a paddle-based juggling robot. It's non-trivial. Yeah, so they could palm the ball. They could start, and then they started to get fancy, right? They wanted to start putting these things together. Maybe I want to, I don't know, I don't juggle very well, but you can imagine, doing more complicated things with the robot. But they didn't, those more complicated things started involving things like collision detection, right, with my leg. And they actually did have beams coming in, and they wanted to juggle this side and then this side, and they did all kinds of fancy things with this. But they needed a mechanism for doing that planning, the collision-free planning, with a system that was a dynamical system to begin with, in which they already had feedback control built in. And really, they couldn't, you couldn't, after you've done these mirror laws and thought about it this way, it's hard to go back to thinking about the full state space of the juggling. It feels like you don't want to throw away all that work you've done. So this was a big motivation. If you think about how do you take the feedback control ideas we've been talking about and the planning ideas that actually people hadn't even really been talking about as much back then, and these ideas of planning and collision-free, how do you put those together in a beautiful way, right? And it's hard, but they had a very, very beautiful picture that they put into their work of how you could put these things together. Okay, and I thought I'd actually pull up their picture. So this is their idea. So Rob Burge came in and joined the group. Al Rizzi and Dan Kodacek. They talked about sequential composition of dynamically dexterous behaviors. Okay, and the idea was, instead of planning trajectories through space, like we've been doing with trajectory optimization, with RRTs and everything, they're going to take and compose existing controllers, okay, by, guess what? Thinking about Lyapunov functions. Okay, so this is really, everything's coming together now. You got to get ready, okay? So we got Lyapunov functions, okay? They're going to think about their feedback controller, which they've analyzed on the Poincare map. They have a sense of its base and of attraction, right? And they're going to think about each controller that they have, separately designed, as something that takes a bunch of initial conditions and takes it to a smaller set of initial conditions. That's what the goal of my feedback control, right? And we can be precise about that using the language of Lyapunov functions. If I can find the region of attraction, right, and then I know that after some time I'm going to go downhill on the Lyapunov function. Okay, the Lyapunov function can give me metrics for these pre and post conditions. Okay, but this beautiful picture is the feedback control as a funnel that takes things from logical state space to a smaller bit of state space. And then the idea that's very powerful, I think, is that if you can just take multiple feedback controllers and sequence them together in the right way, and have the output of one feedback controller feed into the input of another feedback controller, then you can do more than you do with any one feedback controller by itself. Okay? And maybe if you're looking back down at state space, then what you could do is when you had initially had one controller here that just covered a little bit of state space because it was maybe a local controller or something, maybe you can start building controllers that are valid for a bigger part of state space by composing these things together. And we know that the reachable set, or the pace of initial conditions that you can recover from, might not be some simple circle or something like this. Maybe it's some complicated picture like this. But with enough funnels, right, you can potentially fill the space. So there's this big idea, this big idea of trying to take feedback controllers and doing planning with the feedback controller instead of planning with the trajectory. Okay, so today it turns out that's going to connect really nicely to the stuff we've been thinking about with trajectory planning and with Lyapunov functions and everything. It all comes together in a nice way. One of the things actually that was interesting is they proposed this before they had the tools to really build and verify Lyapunov functions, right? They didn't have sums of squares algorithms then. If you go farther into the paper, you'll see that they have scatter plots of data, which they drew circles around and said, they ran it on the robot a bunch of times. They got scatter plots of when it worked and when it didn't work, and they drew a circle around it and said, that's my beginning of my funnel, and that's the output. Nowadays, we can call sums of squares, for computing those, and that's a difference. Yeah.
Do we need to assume something on the bandwidth of the controllers so that they don't cross-talk with each other?
So always yes in some sense, but so there's just a question of how much you have to model in your dynamics. That is just another piece of the dynamical system. So if you were to assume that the bandwidth was infinite and find out that caused a mismatch between your model and the real robot, then I would add more richness to the model to encode the actuator dynamics, for instance. Right? So that's always an exercise in all of these problems, and most of the time where you can get away, like the time constant of the ball moving and the paddle moving are much lower than my actuator, but you're interested obviously in the space where the actuator dynamics matter. So you'd be finding the place where the actuator dynamics have to be in the equations of motion. Yeah, and we do that for some problems. It just depends on the time constant of the problems. Okay, so they put this together and did cool stuff, right? So this is their sequential composition piece. For instance, you could plan and palm and catch balls, and you could see I had to do some work to find these videos, but I've definitely seen videos of them bouncing, through and over poles, which is sort of under the leg, and things like this. It works. They were able to make it work up to the limitation at the time of being able to estimate those funnels from data. Okay. But the big idea there is that these Lyapunov functions that we've been talking about can actually connect back and be a useful tool for planning. Okay?